Now for part 4. In this video, we'll do 3 proofs of injective functions along with supporting proofs. Then we can write an injective function f where x maps to y, where every input in the domain of x maps to a unique element in the codomain y. This means if x sub 1 cannot equal x sub 2, then it must follow f of x1 cannot equal f of x2. In simpler terms, it's defined as a function along with the condition no two inputs from x maps to the same output in y. Refers back to the previous video. Essentially, we said another way of considering the operation of an injective function. If two inputs happen to produce the same output, then what must be happening? Those inputs must actually be the same. First off, ladies and gentlemen, we want to show f of x equals 2x is injective. Then, just consider what we just said. To show, we'll use a proof technique called contrapositive, such as, in the context of this example, proving a conditional statement, if not P, then not Q, by proving its logical equivalent, contrapositive form, if Q, then P. But you'll also see in other proofs the statements are switched, such as if Q, then P is the conditional statement. For example, to prove the conditional statement blue 2, we can prove its contrapositive blue 3. F of x1 equals f of x2 implies x1 equals x2, which, as you'll soon see, is easier to demonstrate mathematically. Since we formed both statements, we can prove the contrapositive directly using algebra. We can conclude, since the contrapositive is logically equivalent to the original statement, proving the contrapositive proves the original statement. Let's get started. We want to go in the direction of the yellow arrow, returns blue 3, with just a notation adjustment for simplicity. Column 1, it naturally follows f of a equals f of b. Then 2 times a equals 2 times b. Column 2, divide each side by 2, which just leaves us a equals b. Since the white boxes are a match, we've shown 2 times x is injective. Because we proved the contrapositive, if Q then P, we have also proven the original statement, if not P, then not Q. Once you think about it, for an injective function, if we have f of a equals f of b, the only logical conclusion is that a must equal b. Observe column 3. Which is just a heads up for what's coming very soon. If we divide a number with itself, here's what's going on. Any number that has a power of 1 is the number itself. So we can rewrite 2 over 2 as 2 raised to the power of 1 minus 1, which is just 2 to the 0, which just equals 1. Next, let's show f of x equals 2 times x plus 1 is injective. We go in the direction of the yellow arrow by using blue 3. First column, we do a similar setup. We have 2 times a plus 1 equals 2 times b plus 1. Then subtract 1 from both sides, which returns a result that should look very familiar. Column 2, divide each side by 2, which just leaves a equals b. The white boxes are a match. Thus, we've shown 2 times x plus 1 is injective. In both examples, we directly proved the contrapositive using algebra. In our previous video, we mentioned we have a proof. The exponential function e to the x is injective. First off, let's prove the division property of exponents, which states for any non-zero real number a and any integers m and n, we have the equation a to the n over a to the m equals a to the power n minus m, which we named blue asterisk. Then consider the expression a to the p over a to the q for any integers p and q. First column, a to the p just means a times itself, p times, and a to the q means a times itself, q times. Then we have a to the p over a to the q equals a times itself, p times, over a times itself, q times. Column 2. If p is greater than q, there will be p minus q factors of a remaining in the numerator. We also have the case, if q is greater than p, there will be q minus p factors of a remaining in the denominator as 1 over a times itself q times. Would you agree? Then the remaining factors in the numerator, a times itself p minus q times, results in a to the power of p minus q. Therefore, a to the p over a to the q equals a to the power of p minus q. Since m and n are also any integers, the white box holds. Therefore, the division property is proved. But for what's coming up, we need to have n and m hold for any real number exponents. In another video, for your interest, we'll prove the division property for all real numbers, which includes the rational and irrational numbers, which includes the integers, because we can write all integer numbers as rationals. It follows the zero power, which is like a corollary because it naturally follows from the division property, any number x raised to the power of 0 equals 1, for x cannot equal 0, named yellow asterisk. Then, referring to the division property, which we just proved, x to the n over x to the m, we know equals x to the power of n minus m. Sound good? If so, in the first column we have, for any integer a, x to the a over x to the a equals 1. Then in column 2 we know we can rewrite as x to the power of a minus a, which equals x to the 0. Since x to the 0 equals x to the a over itself, x to the 0 must equal the number 1. We're done. With one last clarifying statement. The case 0 to 0 is excluded because division by 0 is undefined. Very nice, because we'll use these proofs to support our next proof. With the condition, like we said, in another video, we'll prove the division property for all real number exponents. We have to watch what we promise, because this season is supposed to be about linearity. Nonetheless, we'll show f of x equals e to the x is injective. For the benefit of those who don't know, briefly, Euler's number e is a mathematical constant, approximately 2.71828. It's an irrational number, which makes it almost impossible to reason with it. No, which actually just means we cannot write it as a fraction, as an exact value, such as the number 0.75 equals exactly to the fraction 3 over 4. Euler's E plays a key role in calculus and describes continuous growth and decay, making it a fundamental constant in mathematics and science. More discussion about irrationals and Euler's constant E for another video. Then we have f of x equals e to the x in the white box. In the blue box we have f, where any real number maps to any positive real number. The codomain is positive because the constant e is a positive base, and a positive number raised to any real power will always result in a positive number. Such as when x is negative, e to the x becomes a positive fraction less than 1, approaching 0 but never reaching it. Recall, blue 2 is the conditional statement. So let's get started. Notice, we'll do exactly the same type of proof, going in the direction of the yellow arrow using the technique of contrapositive. In column 1, we've set up the proof the same way as before. We have e to the a equals e to the b. Then divide each side by e to the b. In column 2, we have e to the a over e to the b equals 1. But we know from the division property, the blue, red, and green asterisks, we can rewrite it as e to the power of a minus b, which just equals 1. The red and green asterisks refers to the division property for all real numbers, which we'll prove coming up shortly. Because any number raised to the power of 0 equals 1, and Euler's z is greater than 1, it must be that x equals 0 at the yellow asterisk. So, solving for the exponent, we can set a minus b equals 0, add b to both sides returns a equals b in the white box. Since a and b are any real number x, therefore, we've shown e to the x is injective. We are done. Very nice.